Hey everybody, so this is the solution video for Worksheet 6.3. We're going to be talking about exponential equations and inequalities and how we can solve those. So the first one we're going to start off with is an exponential equation. 2x is equal to 8. So one of the first things we're going to want to do when we're faced with an equation that has an exponential function in it, we know that because we'll have a real numbered base and then we'll have some variable as an exponent. The first thing that we're going to want to do in this case is we want to isolate the exponential. So if we have to add or subtract any constants or divide by any coefficients, we'll want to make sure we do that first. In this case, the exponential is already been isolated, but still it's worth noting for future examples. So first step, we'll make sure that we isolate the exponential. The goal here is to get the exponential function on one side and then constant terms on the other side, just like we have here. So here's our exponential, and here we have our constant term. Now once we've done this, we've got two options. So now we have two options. And I say options, but it's really going to depend on the equation. One possible way that we could attack this is to see if we could write both sides as exponentials with a common base. So in this case, on the left, we know that we have 2 to the power of x. So if possible, could we take 8 and write it as 2 to the power of something? Well, in this case, this is going to work out because we know that 8 is 2 to the power of 3. So we could say, well, we'll rewrite 8 as 2 cubed. Now, in order to maintain this equality, the only thing that can be true here is that these two exponents have to be equal to each other. The bases are the same, so x would have to be equal to 3. So we can equate the two exponents at this point, which now would give us our solution that x is equal to 3. So when we can do this, when we can rewrite the constant as an exponential with the same base as our others, this really works to our advantage. Now, this doesn't always work, so this second option is sort of our fallback. If that doesn't work, what we could do is we could just go ahead and take the ln of both sides and use properties of logarithms to solve for x. So it's kind of overkill with this one, but just so you can kind of see how it works. So we're going to go ahead, we're going to take the ln of 2 to the power of x, and then we're going to take the ln of 8. Now we know that we can take that exponent out in front of our log by properties of logarithms, so we can write this as x times the ln of 2 is equal to the ln of 8. And the ln of 2 is just a number, so we can go ahead and we can divide both sides by the ln of 2. And that gives us x is equal to the natural log of 8 divided by the natural log of 2. And this turns out to be 3. So we've got two different options here. Clearly the first option is quicker if we can utilize it, but if not, 2 is a nice sort of tried and true method for any exponential equation to solve. So with this in mind, let's go ahead and give b a try. So we've got a slightly more complicated exponent, but other than that, it's kind of the same as part A. So for this one, what we'll do is we're just going to use the first method here, which is we're going to take both sides and rewrite them as exponentials with a base of 2. So we've got 2 to the power of 4x is equal to 2 cubed, which means that 4x would have to be equal to 3, which means that if we divide both sides by 4, this implies that x is equal to 3/4. And that would be our solution for this one. And we're not going to bother with the other one. We know that would work. This one's just quicker, so we can move on to the next one. All right, so for part C, we've got 3 to the power of x minus 1 is equal to 27. So can we write 27 as 3 to the power of some number? Yes, because we know that 27 is 3 cubed. So we can use our first option, and we can say 3 to the power of x minus 1 is equal to 3 cubed, because we know that 27 is just 3 to the power of 3. Which means that x minus 1 has to be equal to 3. We add 1 to both sides, and this gives us a solution that x has to be equal to 4. And that's how we can do that one. Excuse me. So now here in part D, we have to consider other options. So we've got 5x is equal to 2. Well, I'm sure there's some exponent we could use to write 2 as an exponential with a base of 5, but it's not obvious. So we're going to go ahead and we're going to use that second option. And what we're going to do is we're going to go ahead and take the ln of both sides. Take the ln of 5 to the power of x. We'll take the ln of 2. And we'll utilize properties of logarithms. So we can write this as x times the ln of 5 is equal to the ln of 2. We'll then divide both sides by the ln of 5, and we get that x is equal to the ln of 2 divided by the ln of 5. By the way, there is no property of logarithm to combine this, so please do not, I'm going to write this in red because I do not want you to do this, but this is not equal to the ln of 2/5. Again, not. Big capital letters, but it's a mistake that sometimes you get. You want to try and use properties of logarithms where they can't be used. So this is not the case. This is the only solution that we would use in this case. Again, if you're asked to round it, you could type it into your calculator, but this is a nice exact answer, and this is most of the time which you'll be asked to find. All right, so now we'll consider part E. It seems very similar to part D, except we've got -2. Now there's a couple things we're going to notice here. If you are paying attention, you might look at this and say, wait a minute, 5 to the power of x, that's an exponential. It's never going to be equal to -2 because -2 is not in the range of this function. So we may notice that -2 is not in the range of y equals 5 to the power of x. If you think about what this graph would look like if we were to sketch a graph of 5 to the power of x, it's exponential growth, and it never drops below the x-axis, so we never have this function equaling -2. So that's one thing that we would note, that maybe this doesn't have a solution. Even if you didn't catch that, if you started working through the problem, here we would have to try the second option. We'd take the ln of 5 to the power of x, and then we'd try to take the ln of the other side, and hopefully at this point you'd also realize that, wait a minute, you can't take the ln of a negative number. -2 is not in the domain of the ln of x. We're not allowed to take the ln of a negative number. Remember, it's got to be strictly positive for logarithms. So because of this, we would conclude that this problem has no solution. No solution. Okay, so that makes that easy. So now we can move on to F. So in problem F, again, there's no easy way to write 5 as an exponential with base 3, so we'll go ahead and we'll use the technique of taking the ln of both sides. So we'll take the ln of 3 to the power of 2x. We'll go ahead and we'll take the ln of 5. We'll use properties of exponents to rewrite the left side as 2x times the ln of 3 is equal to the ln of 5. Now you could do this all in one step, or you could break it up. I'm going to do this in 2 steps. I'm going to divide both sides by the ln of 3. And while I'm at it, I'm going to divide both sides by 2, because I want to get rid of that 2 as well. So that's just going to leave me an x on this side, and then the ln of 5 divided by 2 times the ln of 3. Now, just to warn you, WebAssign might be kind of picky with this, and you may want to note, this is a perfectly correct answer, but sometimes we know that WebAssign can be a little bit finicky about things. We can use properties of logarithms here. So we're going to go ahead and we're going to make this coefficient 2 an exponent of 3 using properties of logs. So let's see what happens if we do that. So this is the same, and these are equivalent answers. So we'd have the ln of 5 divided by the ln of 3 squared, which would be the same as the ln of 5 divided by the ln of 9. All three of these are the exact same value if you type them in your calculator to get an estimation, but I have a feeling sometimes WebAssign will prefer this last version, the ln of 5 over the ln of 9. It looks cleaner anyway, but just so you know how that works. Okay, so now we're going to move on to number 2, which is an exponential inequality. When you run into these inequalities, it might be a good idea to go ahead and first think about this in terms of a function greater than or less than 0. So I'm going to go ahead and I'm going to move the 53 to the other side and think of this as e to the x minus 53 is strictly greater than 0. So we're going to kind of work with this second version throughout this inequality process. So for our first step, we're going to go ahead and we're going to find the zeros. So this is going to sort of be our function right here, what's isolated. So we're going to go ahead and we're going to take e to the x minus 53, set it equal to 0, and then we're going to solve for x. So first thing we'll do is we'll add 53. So that's going to give us e to the x is equal to 53. And now we need to solve for x. We do that by taking the ln of both sides. So we take the ln of e to the x. We take the ln of 53, and we're going to get, we could skip this step, but I'm going to go ahead and show it to you anyway. We'd move the x out front. We'd have x times the ln of e is equal to the ln of 53, and we know that the ln of e is just equal to 1. So we're left with x is equal to the ln of 53. So this is the 0 that we were asked to find in this first step. The next step that we're going to do is we're going to set up a sign diagram. So in step 2, we set up a sign diagram. So this is what we're kind of getting used to doing for inequalities now. So sign diagram. Now the only point we have to put on this sign diagram is this 0 that we found here. Now depending on the inequality, you may have more than one 0, more than one critical number, but in this case this is the only thing that we have to plop down on here. Now the ln of 53 may not know where that goes. Since we're going to have to pick test points, it's usually a good idea to get an estimate of these. So typing this into your calculator, this is about 3.97. So we're going to use that when we create this sign chart, or the sign diagram. So I'm going to go ahead and I'm going to set that up, and that's going to go from positive infinity to negative infinity, and we're just going to plop right here in the middle the ln of 53, which we know is approximately 3.97. So now we have to pick our test points. So I'm going to go and I'm going to pick 0 from this side, and since this is a little bit less than 4 over here, I'm just going to be safe. I'm going to pick 100 because it's easy to work with. Now remember, with these sign diagrams and testing points, all we're interested in is whether it's positive or negative on that interval. So this is our equation up here, that e to the x minus 53. So we're going to use that in this process. So if f of x is equal to e to the x minus 53, then for x equals 0, our first test point, we're going to have e to the 0 minus 53. And e to the 0 is 1, so we know that this is going to end up being a negative number. So on this interval, our function is going to be negative. And if we plugged in 100, well, e to the 100 minus 53, that's going to be a positive number. E is a number that's going to be much larger when we raise it to the power of 100 than negative 53. Which will give us a positive. So we're positive on this interval. And again, we know that this point right here was a 0. Okay, so now we just have to interpret our inequality. So remember, what we were asked to find here is when is this function strictly greater than 0? And if we look at this, it's going to be strictly greater than. We're not going to include the 0 because it's strictly greater, and then we're going to include all of these points all the way off to positive infinity. So our solution is going to be the interval from the ln of 53. Again, we're not including that, all the way off to infinity. And that would be the solution to this interval using interval notation. Okay, so this process will work for any inequality. Some are obviously more complicated than others, but hopefully that'll at least get you started. Okay, so that'll do it for this this video, and I'll see you all next time.